Okay, can people hear me at the back? Hello? I can't believe this. This is... Hi, at the back, can you hear me? Can you hear me at the back? Can you hear me at the back? Yes? No? Okay, we seem to have the same problem this week, which is unfortunate, but we'll see how we get on. We also seem to have only one screen. Can people over on the, let's see, the right side of the auditorium, from your point of view, can you see this okay? Yeah. No? Oh, okay. Too much of an angle. You might want to move. Apparently this doesn't seem to be working. So go figure, they were supposed to have fixed it. They fixed it by reducing redundancy. All right, so welcome to the second week. The topic of the week is regression. It's a form of supervised learning. For some people, this may be review. I think a lot of you, possibly all of you, will have seen some aspects of what I'm going to cover. The idea behind this is to develop certain things to set the scene for various other things that come later, and just also to explain linear regression, because although it's a long-standing and sort of rather humble technique, it's actually very useful and should be part of everyone's toolkit when they're doing machine learning data mining. So just to cover that, we have to outline the basic task, talk about how linear regression addresses and solves that, talk about how the fit works, mention briefly nonlinear issues, and talk about why that's possible in this setting. And finish with talk about the parameters and how they get estimated, and then finish by talking about an interesting version of regression. Now, when I gave this lecture previously, which was the first time I'd done it in this form, I got some feedback that it was fairly dense. There's quite a lot of material. So what I've tried to do is, I've certainly taken out some material. I've tried to reorganize the material, but I've left in something. I've left in some things that are not on our main path. Not on our main path. I might just actually sit down and give up on this. How's this? Is that okay? Can you hear me at the back? People at the back? Thumbs up? Okay. Right, I might go with that. This one just seems too hard. They were supposed to have fixed it, but they haven't. All right. So now I'm sitting down. Maybe I can fall asleep with the rest of you. Okay, so just on this point here, I have left in some material, but I consider it not on the main path. The reason I've left it in is because A, it's good background, and B, I think just having it there, you may find, if you find it a bit confusing at the moment, I will talk through it. If you find it a bit confusing, you can leave it for the time being. But you may find later on, when you come back to it, it becomes much clearer what it is and why it's there. So that's a bit of explanation. So I just put this in the title bar. So any slide with an asterisk in the title bar, that's what I'm referring to. Okay, so I talked a lot last week. Last week, remember, the goal was to essentially outline the parameters of the whole course and what we're going to do. So I talked a lot about classification there. So classification, the task is predict a discrete value, like +1, -1, or red, blue, green, or buy, will not buy, anything of that nature. But we also mentioned, so many tasks are like that. I talked about the fact that, first of all, supervised learning is very widespread, and many tasks fall into supervised learning. Not only that, they are actually classification tasks. So classification is probably, it's safe to say, the dominant paradigm. However, in many cases, the most natural thing that you want to predict is a number, usually just a scalar, but it could be a vector of numerical values. And then the question is, well, how can you set that up? And it actually turns out that the way you can set that up and solve the problem is, I think it's safe to say, the most canonical method in all of statistics, data science, machine learning. So that's what we're going to do tonight. So just to set the scene, I'm not sure if I've showed you this data set before. This is a classic data set. By the way, a lot of small data sets that I sometimes use are found in a standard repository at the University of California at Irvine. So you can go and download these. So when I say CPU data set, it's already in some distributions of machine learning software, but if you go to the UC Irvine, that's the first UCI. If you just Google UCI data set repository, something like that, you're going to find a few hundred of these. So that's your first point of reference if you want to get some, get some data, get your hands dirty. So this is exactly like that. So we have, I'm not sure if these are all of the, actually no, I think one of the features at least is missing, but that's not a problem. It's not important for this. So we have data. These are old, this is an old data set, so these are actually configurations of, I think, motherboards, or actually the CPUs on them, I don't remember precisely. The dependent variable, the thing you're trying to predict, is just by convention, very often in the way these data sets are formatted, by convention we're going to look at the rightmost column for the thing we're trying to predict. So here it's called performance, it's abbreviated like this, and you see it's numerical. So all the way down, so it's a small data set, just over 200. Now, it turns out as well that in this data set, all of the other features are numeric as well. By the way, I highly recommend anytime you get a new data set, if it's absolutely massive, it's not as easy, but certainly if it's small like this, just run it through, put it in Excel or your text editor or whatever it may be, and just run your eye across this, because you very quickly start to see some things. I mean, you'll notice here, for example, well, there are only 5 values that I'm showing you, but if you scrolled through this this column here, you'd see everything was in powers of 2. Now, you know from the header here that that's not surprising. You also know here that it wouldn't be surprising to see things in terms of, well, this tells this tells you the date of the age of the data set. These days, this would be GB, I guess. But anyway, so you can see multiples, powers of 2, and I think this is the same here as well. I'm not sure what these are, but it may be. So this doesn't necessarily, no, this doesn't look. But you can also see the range, right? You can see the magnitude. Now, this is not the main topic of the night, but if you're going to go on and do this stuff, it's surprising how often people fail to do this. And just a very quick eyeball, obviously if there's millions of columns and hundreds of millions of rows, like, if you're working for a web company, you're not going to be able to do that. But, a lot of the time you can just even, look at the top of the file, look at the first few columns, and any sort of weird stuff should just jump out at you, even in this very basic formatting. And there are lots of tools now that you can actually, do plots and histograms and whatnot. Very strongly recommend you get into that habit anytime you're looking at data. In fact, you should be excited anytime someone gives you a new data set, you say, aha, let me check this out, see what's going on. And the reason why that's important, well, there are a few reasons, but one is it'll tell you very quickly if there's some weird stuff, but it'll also reassure you that your initial thoughts about the task and the kinds of learning models to be fitted in the learning problems are sort of coherent with, so your expectations of what you're about to do are coherent with the data, because if you see something that's different from that, you're going to have to do something else. So Anyway, that was a bit of a digression. Let's get back on track. Okay, so why am I showing you this? Well, just to reiterate, it's a data set where the thing you're trying to predict, the output, remember we're always trying to predict stuff, or we're nearly always trying to predict stuff. Certainly in supervised learning, we're trying to predict stuff. So stuff you're trying to predict is numeric value, scalar value, and that's over here. And all of the other features are numeric. Now, you could have got a data set where that wasn't the case, right? So some or all of these may not have been numeric. So they could have been text strings, or they could have been, something else. So where it's the case that the thing to be predicted is numeric and everything else, all the features are numeric, then linear regression is exactly the first sort of thing you might think of. Or possibly not linear, but certainly a regression type application. So if, in fact, you did happen to run a linear regression, you might find something like this. I'm pretty sure I ran this on the whole training set, so it's possible to observe a few things. First of all of the features, I think all of the features, yeah, all of the features in the data are included in the model. Each one is multiplied by this number here. They're all positive, it so happens, apart from this one. And then there's an offset here, which happens to be negative. So this is a linear equation, linear regression equation. So this is the kind of thing. Now, if this wasn't the kind of thing you wanted, then linear regression is not what you're about to do. So that's just setting the scene. Now, a lot of machine learning, as I said last week, inherits stuff from AI. And in AI, we have a lot of symbolic representations. And in that case, it's very natural and straightforward to formalize the problem as a kind of discrete optimization problem. And one way that people often refer to how that is done is searching a space of something like Boolean functions. We call those hypotheses. Not actually sure why, it's just a historical term. And there are all kinds of languages that you can use for hypotheses. We'll talk about trees later. We may talk about graphs. But if you're talking about the kind of model that would be appropriate for the data set we just looked at, you're talking about wholly numeric representations. So the most natural way to think about machine learning, anything that is cast in this as this kind of task, is searching or optimizing within a space of functions. So the problem now becomes what kind of functions, how do those functions get evaluated, and various other kinds of issues. So the kinds of functions that you would naturally consider are mathematical linear equations, neural nets, which are also essentially, when you boil them down to their basic elements, also sets of equations, nested sets of equations, but still. And there are many other kinds of functional forms that you can consider. Now, in both of these settings, the discrete and the numeric, I haven't mentioned probabilities, but they could be stochastic. They could be probabilistic as well. Okay, so in the setting, the classic thing, certainly from the point of view of statistics, it's classic because it's been around, well, in some form or another for over 100 years as linear regression, and prior to that, the sort of basic idea, the line of best fit idea has been at least around for over 200 years. For machine learning, there is a whole class of learning linear models, which is not actually linear regression, but the kind of model that you get is very similar. We'll talk about that later. The differences are important, but so many applications, very widely used. These days, everyone wants to do deep learning, and it's not not a coincidence that the whole idea of neural networks, artificial neural networks, is essentially based on this sort of function model fitting. There's also the issue of nonlinear regression. There are different ways to do that. I'll mention extending the setup in a sort of minimalist way, which has advantages and disadvantages. We already mentioned multiple multi-layer, potentially deep networks. There are also rather interesting and useful hybrids that get less attention, things like tree-structured regression models. That's essentially a piecewise linear approach, and there are many other piecewise linear approaches using things like splines and so forth. And then, so I won't talk about that this time, but I will fit that in later. And last but not least, the thing at the end of this lecture, which is local regression. Okay, so we've got a linear equation. The outcome is going to be a linear sum of the feature values with the appropriate weights. And just in passing, let me notice that when I say regression, this is an overloaded term. People often refer to the process of learning as regression, like, oh, I'm going to do a regression, or it's time to fit a regression. I guess strictly speaking, it's just the equation itself that is the regression. So here's an example. Here we have a bunch of, okay, so I haven't labeled the axes. Let me just be clear. I'm getting really fed up sitting down. I'm going to move around. Sorry about this. I'll just kind of jump up around because I just cannot sit here all night. Okay, so here we have on the x-axis a bunch of values, and then we have a single dependent variable, the thing we're trying to predict, on the y-axis. And you must have seen something like this before. The red dots indicate the data points. So we now have a coordinate representation for data. So x, every x value in the data set has a y value. So what's the problem? Well, the problem is to find a model, it must be a linear model. In this case, it happens to go through the origin. That's not required. But straight off, we can make some observations. We can note that the expected value of the output given the input is of a linear form. So I'll talk more about this. Has anyone never seen expectation before? You all know what E is in this case? There'll be some examples going through. Anyone? No? Expected value, you're all clear about? Good. So we have a notional function here of x, and because there is because the line in this case goes through the origin, we can just say there is a single parameter, this parameter b. So this would be the regression coefficient. You can also think of this just as the slope of this line, and the problem is to find this b. Now, according to this version here, the expected value of y given x is linear. So what this means is, in effect, that we assume or we hypothesize or we imagine that this data has been generated using this hidden model. The regression model is the thing that generated the data. And our task is to, and we assume that there is some unknown parameter b, and our task, or the learning algorithm's job, is to find an estimate given the data. And we already said that it has to be a line of best fit, so that kind of tells you what the criterion is. So we're talking about numeric attributes, numeric prediction. Now, in general, we could have more than one independent variable. So we're going to denote these x1, x2, x up to xn. All of the variables we suppose are going to be necessary in the equation. Now, I'll come back to this later on, but I guess a couple of observations. One is that could cause you problems. Right? So if this is your data set, you have n columns or n variables in your data set. If you're going to fit a linear regression, all of them must be in the model. Now that could be good, that could be bad. It could be bad. Actually, tell me any offers. Why could that be bad? Overfitting. What do you mean in this context by overfitting? Okay, and why? How does that relate to the using all of the features? You're right, but how does that relate to the feature idea? Okay, so what he was saying, for those who didn't hear, is overfitting, right? So that could be one problem. How does that relate potentially to the fact that you put all of the features in the model? Anybody else? There might be errors. Yes, exactly. There might be errors. And if you put all of the features in, you're going to find a coefficient, and that could actually, you'd actually be better off throwing it away. One way of throwing it away is setting the coefficient to 0. You might get lucky, and the coefficient would be set to 0, but you might not. There's another problem. There's another problem with having to fit all and only the features that are in the data. Fit the model using all and only the features that are in the data. Any ideas? Yes?
They can be one feature can be composed by other features. For
That
example, area, and you have length and depth.
Yes, excellent. So there could be a dependency. That's correct. That's a more sophisticated answer than the one I was looking for. The thing I'm looking for is a bit more of a common sense thing. Hard to explain? Yes, that could be true. But I'm looking for something very elementary. That's true. That's sort of related to what he said. Maybe my question is too elementary, so I'll just give you the answer. You may not have in your data all of the features that are required to get a really good model of the output variable, right? So you may be missing an important feature. In that case, there's not much you can do with the learning there's not much you can do at the learning algorithm level. You either have to go and get that feature and measure it and put it in the data, or you have to go to a new algorithm. So it is a consequence. It's a consequence of the assumption that all and only of the features are adequate to fit a high quality or a good quality linear model. Okay, I think we all know that the weights are calculated from the training data, and maybe it's not immediately clear, but let me just explain this. So what we have here is that each of these B's is multiplying the value of the feature. So once we have the B's, they're fixed. What can vary, and that's denoted by this superscript here, right? So 1 means index one of the training set, or in fact, indeed, some test set to be predicted. So that varies, the feature value varies, and the coefficients are fixed. So the prediction, in this case for example 1, is the value of the feature, each of the n features. By the way, I'm going to swap around n and other indices freely. Apologies for that. So BI is fixed. BI is fixed for any piece of data. XI, the value of XI, that variable will change. So when we have this set up, we can think of the problem. I'm going to have to sit down again. This microphone is very flaky. I'm going to jump up and down. I'll sit for as long as I can, then I'll jump up again. So here, what we're seeing is, so this is the model. Okay, so we have a bunch of coefficients, n plus 1. By the way, the plus 1 is due to the homogeneous coordinate argument that we had in last week's slides. If you're not sure about that, you can go back and check. It's simply a dummy variable that corresponds to the intercept value. Okay, so we have this number of coefficients, and then we have m data points. And so if we have these values, these coefficients, the BI, and we obviously have the values for all of the xi's, and we have all of the values for the xi for the jth example, and we obviously have the class value, the output value for the jth example. We go through all of the data, we do this weighted sum, that gives us a scalar value, which we subtract from the known value, we square that, and over the entire data set, whatever this data set is what we're going to call squared error. This is a reference ahead to what we're going to be doing. The coefficients can be derived. So at this point, we haven't said anything about that, but we'll just say here that the coefficients can be derived. There are actually many ways of implementing this. We'll just look at the sort of mathematical setup of it. You probably heard about this. If there are more data points than features or attributes, you can do this. This is approximately correct. It's certainly a good rule of thumb. And the point here is that this whole setup defines what's called ordinary least squares regression. There are other versions of regression. In fact, I haven't even given you the whole specification of why this is ordinary least squares regression. And by the way, that's true for pretty much everything that I'm going to be talking about tonight. If we were doing this in stats, we'd spend a lot longer doing this, and we'd sort of dot all of the I's and cross all of the T's. I'm afraid I'm just going to not do that. So any of you who are from a stats background, I apologize. I'm skipping over some important details, but hopefully what is being presented is at least consistent with those important details. If it's not consistent, let me know. All right, so here are two input variables. So we have x1 and x2 this time, and instead of a line, we have a hyperplane. So here the red dots, again, are our data points. And this time we're showing, we've dropped a little distance or dispersion bar showing you how far above or below the plane the actual point is. So these are the differences that will be calculated for each of the, so here we had 2, let me just flip back, so we have 2, so we need to calculate this distance, and so this will give us the position above or below the plane, and then when we subtract the y value, subtract from the y value, that's going to give us the value of this vertical bar. And in general, we can have, if your imagination stretches to high dimensions, you can imagine what that hyperplane would be and what the distance from that hyperplane would have to be for all of the data points. All right, now at this point, we could just dive into the learning algorithm, but I thought it might be productive because a lot of the ideas, I think, only really make sense when put in the context of the background, the sort of statistical background, if you like. I thought we'd step back and just go through some ideas. This is the only time in the course that I'm going to do this. Partly because I don't think it's necessary in other areas or it would take too long. Also because I think a lot of you know some, possibly all of this. So if you know all of this, I'm sorry, you can either go and take a break or do something else while we go through this. But I think for completeness, to make this course and this lecture in particular self-contained, it is useful to do that. Okay, so just very, very much off the top, we're going to sort of freely use ideas from probability and bits of things from statistics. Probability is nicely thought of, I think, in terms of machine learning, at least when we're ultimately wanting to do AI, as going from populations to samples. Now, in machine learning, because we're programming everything, it's very natural to, and particularly these days when we have some really nice probabilistic programming languages coming on the scene, it's really natural to think about generating populations, generating samples, simply by writing down something that can be computed. So we can generate all kinds of data sets according to various weird and wonderful probability distributions, probability models. Now, in terms of those samples, that is a process that we could think about either mentally or computationally as deduction. It's deductive reasoning. And it's sound in the sense, just like a programming language, that when you write down a well-formed probability density, then all of the data that you generate, the samples that you generate, are derived from that. And if you're not sure about that, don't worry about it. It just means you know what the distribution should be, you know what the density should be. Every data point is in accordance with that distribution. So that's like you're playing a sort of, you're generating data, you have this omniscient role. Now, actually, in machine learning, what you typically want to do, so this is fantastic for doing things like modeling, testing out ideas, all that kind of stuff. In general, you're not doing that. You're doing the opposite, right? So you don't know what the density is, or you don't know what the probability distribution is. In fact, it may not even make sense to think that there is anything corresponding to a well-founded distribution, right? So if you're, if you work at Facebook, does anyone here work at Facebook? If you work at Facebook, you have a sample space which is getting on for the world's population, right? So, and what kind of probability distribution covers all humans in the world, or even 25% of them? It's just unbelievably complex. Who generates all this stuff? I mean, how can you possibly think that there's a mathematical distribution behind that? Actually, maybe there is. Maybe it's much more simple than I'm pretending. Anyhow, the basic problem is the opposite. It's inductive. You're given a sample, you don't know what the density is, you don't know what the model should be, you have to make educated guesses. And in a logical sense, nothing is derived. It's all unsound, it's all approximate, and you have to justify it. And that's the reason why we have statistics. And statistics is awesome. Okay, so lots of things go on in statistics. A key thing, I'm not going to go into these, a key thing to remember is that the goals of statistics are often the same as machine learning, but not always. So, there can be different emphases. But there are lots of important aspects of statistics that can help us with our machine learning approach. I'm not going to go into this, but it's always useful, for example, to pay attention to how the data is collected, and I mentioned issues about the data before. So the basic setup we can think of like this. So we're sampling so a sample is from a population, but it's not the whole population. Again, as I said, if you're at Facebook, it's getting on for the whole population. So, there are certain caveats. But it may, in general, be safe to assume that it's not the whole population. So you have to start making some assumptions. One assumption could be that if the population is pretty homogeneous, like every time you sample, you're going to get essentially the same measurements back, then you might not need a lot of data. Okay, so here's an example which relates to work by R.A. Fisher way back. Or, if that's not the case, then you have to have much more data. You have to gather enough data to basically get a good representation of the kinds of complexities that are in this hypothesized model, as I mentioned when we're doing this inductive step. So sampling is a way to get conclusions without having to actually measure everyone in the population. And obviously the conclusions are not completely accurate. And this is the sort of statistical version of the hypothesis that I had at the end of last week, which in machine learning terms is called the inductive learning hypothesis. So this is just another way of saying the same thing. We assume that if our sample is close enough to the population that we're trying to infer stuff about, then we're okay. If it isn't, then we can't, and you can get into deep trouble if that's not the case. So what do we want from a sampling method? Well, We certainly don't want our sample to be collected with any kind of systematic bias. All right, so if that's the case, there's a big problem, because when we come to apply this, and remember we want to do machine learning to apply it in a reasonable way, then all bets are off, because if our sample is biased, then we can't guarantee that our predictions will be accurate, because they're drawn from a biased sample. They're trying to fit a model that in actual fact is not reflected in the sample that we drew. So the population assumption doesn't hold. However, and certainly if you are a statistician, you can try and alleviate that by trying to make some determination about how unrepresentative a sample you've got. And the golden rule is, if you have a lot of data, in particular if you can increase the size of your data, then the chance of it being unrepresentative, again assuming that there are not some weird biases or someone's trying to deceive you, then things are better. So random sampling, we've got data that's in a sample associated with a number, so classic way is to put the numbers into a hat and get someone to pull them out. But of course, using a computer, there are no hats, and we're going to use random number generation. And then in the setup, we can get back the elements of the population. So the basic setting is uniform distribution. But we can generalize that to assume some other distribution. We could, if we wanted to, skew it, and here's an example. We could make larger numbers more likely, depending on what you're trying to do. This could be useful. You could, for example, be sampling in terms of something to do with the size of the household, and larger households have more probability of being selected. And this is all very straightforward. So just bear in mind that sampling should not be forgotten about. So once we have the sample, the problem that we usually have is to do some estimation. So we want to calculate a number. We want to look at, maybe we want to calculate the distribution in some way. And we may also want to put bounds in terms of uncertainties around that. So I'm not going to get into that here, but suffice to say that sampling is often done and is pretty reliable. So classic example would be you have, you assume a distribution, and you assume it has a mean, right? So a numeric value, you assume the population mean is mu. You don't have the population, but you do have a sample. And the sample mean can generally be assumed, unless something's gone wrong, to be a good estimate. Some other things that you want to estimate may not be as good in general. So the range of a sample, so range is just the difference between the max and the min value in the sample, is usually, and this should be common sense, less than the actual range of the population. By the way, the range is actually a very useful statistic to get, and again, going to knowing your data, it's always a good idea because it tells you something about the spread. As I said, it may not be the best estimate of the population range, but it's certainly a useful thing to know, so don't discount the range. So what do we mean by a good estimate? Well, so we said that the mean was a good estimate, or sorry, the sample mean was usually a good estimate of the population mean. Well, what actually, or how can you quantify that? Well, again, in words, you can say the following. So if an estimate or an estimator is correct on the average, then it's a good estimate. So for example, if we take lots of samples, and this is where the wording gets a bit complicated, but I don't want to dive into lots of maths because it's a simple idea. So if we take lots of samples and we take the mean of each sample, the mean or the average of those means, sample means, is a good estimator of the mean of the population, right? That's what we mean by the mean is a good estimate. So just reiterating that, take a sample repeatedly, and caveats about take it in the same way, take it of the same size, take the mean, average those means, and that will get you close to the population mean. So there's this terminology about an unbiased estimator, and that's the kind of thing that is meant by an unbiased estimator. So let's actually make this a bit more concrete. So the mean, I mean, all of you will know this, the mean is found as follows: get the total number of a bunch of observations, and then the arithmetic mean is m, which is the total over n. If the data is normally distributed, this is all fine. So mathematically, we can just rewrite this. So 1 over n times xi summed over all of the observations. Again, note that I'm freely changing around n to mean, in this case, observations. So you just run out of indices. Now, you may have, you may know that in your data there are only certain kinds of values, and you can therefore group those, right? So if they're integers with a certain distribution, like in the CPU data, let's say the memory sizes were only like powers of 2, and there were only a small number of them, then we would have a small number of groups. So we would have groups now ranging over I. So if we know that each group, like the number 256 occurs F1 times, and the number 512 occurs F2 times, and so on, then we just multiply these together and over the total. That gives us the mean. Now, instead of frequencies, we actually had relative frequencies. So if we had now, instead of the number of that value, we have the probability Fi, which is the thing we had before, over n, then the mean is just this value here. So xi times the probability of seeing that value summed over all of the probabilities and values. So this is essentially the expectation. So this is the mean value of the values of the random variable function. So the mean value of the random variable. And if the variables are discrete, then we have it like this. So here's your random variable. Here are, it can take on the values xi. So the probability that it has that value times the value summed over all of those values is the expectation. If you have continuous random variables, then this turns into an integral. Okay, that's all very familiar, I'm sure. The other one we should pay some attention to is the variance. So the variance is, we take the total and the sum of squares of these observations. Now, the estimate of the standard deviation, so the true standard deviation, sigma, is estimated by the sample standard deviation, xi minus the mean, so this is the sample mean, square it, sum it over all of these values, divide by n minus 1, take the square root. If you don't take the square root, that's the variance. And again, if you're talking about a normal distribution, this is all fine. Again, if we have grouped data, we have xi for the groups times so this is the group value, this is the number of, this is the frequency in the group. And the point that we get to is in terms of the expectation, here's the expectation form of the variance. So just by, so E of x corresponds to this, and then we have each of the x's minus this squared. So remember that was standard deviation if we didn't take the square root. Don't worry about the n minus 1, that's just a technical issue due to the number of degrees of freedom when you're calculating the sample standard deviation. When n gets big, it's obviously negligible. But here's the point. We can rewrite this conveniently as follows. So we take the expectation of the squares, these are the values, and we take, and then we subtract the square of the expected value. All right. So the way to remember that or think about that is the mean of the squares, that's this, minus the square of the mean. Okay, let me, yeah.
How can you know if amongst your data if it follows a normal distribution to use this formula?
Great question. So the question is, how do you know? So the question is, how do you know that your data follows a standard, a normal distribution? The answer is that you can't in general, unless there's a way of someone telling you. There are ways to estimate it, which are more or less good. You can look at the standard deviation and see how much of the data falls within plus or minus 1, 2, 3 standard deviations of the mean. If the data is normal or approximately normal, most of them should fall within plus or minus 3 standard deviations in a symmetric fashion around the mean. That will give you a quick and dirty indication that it's normally distributed. But I mean, there are other ways of doing it, but that's about as far as I know about. And you could do it that way. Personally, I would do that, but I wouldn't rely on it too much. Okay, so we're heading up towards 7 o'clock, and I want to just do one thing, and then we'll take a break. So we've now seen we've formalized the mean and the variance. Now we're talking about unbiased estimators. We know what an unbiased estimator is. Bias is not good, right? So if there's a systematic bias, we don't want to have that estimator. If we have unbiased estimators, we would also like to have the one with the minimum variance. Unfortunately, we're probably, certainly with more sophisticated estimation problems, so more sophisticated models to do the estimation, not just the mean, we would probably have or expect to have some bias, so there's some systematic source of error in the values that we're computing, and some variance. So the bias and variance together of an estimator can comprise the mean squared error, MSE. So the MSE is the average value of the squared deviations of the thing that you're trying to predict, your estimator, from the true value, usually of a parameter of something you're trying to learn. So here's the formulation. The MSE is the average value of this squared difference. Now it turns out that, and it's possible to show just using what I showed you before in terms of the expectations, that MSE decomposes like this. It decomposes into the sum of the variance of the estimator and the square of the bias of the estimator. So these are two quite different things, but they are related in this way. If the estimator, the bias and the variance has zero error as the sample size increases, then that's what's called a consistent estimator. So the minimum that we can have is 0. Unfortunately, we may not be able to get to the ideal minimum. There's a particular property called the Cramer-Rao bound, which is beyond the scope of these lectures to go into. But suffice to say, the minimum can be bounded by this bound. And so then, that's in terms of the bias. So then MSE must be greater than V min. I beg your pardon, that's in terms of the variance. We're talking about the bias. So V min is the minimum variance plus the bias squared. Now, V min could be the estimator could be biased or unbiased. So it's either, B is either 0 or not. Now, intriguingly, it is the case that if you have an unbiased estimator, it's not necessarily less than, the V-min for an unbiased estimator is not necessarily less than V-min for a biased estimator. So it could be that a biased estimator can actually have a lower MSE than an unbiased estimator. Okay, so the point I wanted to get to is this one, and then we'll stop. So here's the thing. The bias variance forming up the MSE can be formalized as this. So here's the setting, and it's important to remember this because we'll talk fairly freely and loosely about bias variance, but this is actually the way it's properly set up. So we just think about the sampling setup that we've introduced. We're talking about making a prediction. There are many samples of the same size, drawn in the same way. That means drawn at random according to the same distribution with whatever assumptions common between each draw. The error based on this is obviously between the prediction and the actual value. So this is a sample-based approach. So the MSE decomposes like this. So this is the thing that we estimate. This is the true value of the hidden function that we don't know about. We're taking the square of the expected. This is the error. We're taking the square of that. And this decomposes like this. So, and it's actually fairly involved to do this, but you can derive it. So here's the point at which you get to when you do the derivation. Y hat, which is the estimation, minus the expected value of y hat. So this is per sample, and this is over all of the samples. The square of that, the expected value, the square of that, plus the expected value of the estimation minus the true value squared. Now there's one interesting, and it'll turn out practically important observation that we can make about this, and at this point I'll just say this and then we'll stop. If we note that the first term, which is the variance, it does not involve the true value. And everyone see this? So the thing we're trying to estimate, which is the population, so all of the x's in the population will have this value. We don't have access to all of them, but we have the sample estimates. So if we do a lot of samples, and then we take the difference, square it, take the expected value, this does not involve any reference to the true value of the thing that we're trying to predict. So this is simply a statement about the sampling that we're doing and the change from sample to sample of the way that we're doing the prediction. So this might look incredibly abstract and even a little bit obscure, but it turns out that under certain circumstances, there are things we can do to reduce error and hence and so improve performance of machine learning methods by attacking this. There are also things that we can do to improve the performance of machine learning methods by attacking this as well. So independently or together, we can try and reduce the components of the error along the dimensions of both bias and variance. So that will come back in later lectures. Let's take a short break and we'll resume in about 5 to 8 minutes time.
In general, the rule is though be careful about transferring away some of the super strong. So if it's a single variable, you were told or you knew it should be distributed, and you've got something that's like 9 standard deviations of mean.
Yeah, and this is also a matter of reference because it said I'm going to consider everyone as an outlier with 2 or 3 standard deviations. So it's like a
yeah, so the rule of thumb is the properties of the normal distribution. So if you have enough data and it is normally distributed, then 99% of the mass of the data is going to be within plus or minus 3 standard deviations. But that's only true if it's actually normally distributed and you've got enough data. And if you don't have that, then time is going to cause you a big problem. Here's why. If you have time as a variable, then you'll effectively only be able to predict for the same time.
Yeah.
So what you should do with time, well, it depends on your application, but you should, if time is important, like change over time is important, you should turn that into a feature like amount of change since the last observation, or amount of change over, like a moving average over the last 3 or 5 observations. But you need to be careful. It depends a lot on what time, how time is being measured, and what you're trying to predict. Convolutional networks, no, not really. I mean, convolutional networks won't handle time unless you set time up. You may be thinking of recurrent networks, which you can do in a sense, but even then you're going to be getting back to it.
But is there any specific model that is easier to
Time?
Yeah.
There's a whole area called time series prediction, which is, okay, so the canonical version of that is kind of regression. It's called auto-regression, and the simplest version is if I, let's say I have 10, I have a window of 10 times, those are my regression features, like my regression model, it's t minus 1, t minus 2, t minus 10, and then I try to predict the next time. Slide up. And that will work if the next time value is a linear function of this time. That's what you're trying to do. But you have to be careful to make sure that that's actually
The last question. Can you give me some tools how to identify if one feature is different or composed by other features?
there are ways of doing that. It's a bit complicated to explain, but basically you do something we're going to touch on later.
We are going to see this.
Well, essentially, what's going to screw these kind of methods up is if some of the data vectors are it's going to screw up this later on we'll look into that. It's called dimensional architecture. There are ways of determining. Well, basically, we move to a new set of vectors. We move that.
Automatically?
Yes, you move that. But you've moved to a new set of features, so your old features. Basically, take the most important linear combinations of your original features, you make a new feature space, and you do your work in that space. Right.
This is the standard. You always, so you have always have to do that.
Well, you don't always have to do it. If you think or you know that you've got dependencies, you can do a check. Like, for example, you can do what's called feature selection. I'll talk about that later. Very simple way to do it is just look at combinations of features. If you put them in the model and then make the model worse, then they could be linear combinations. Take them out and just do that.
These are that penalize already removes the dependencies.
Yes, if you find that there are certain ones that look bad, take them out. You just run the algorithm repeatedly. So it works as long as the data is matchable.
And in this dimension reduction, if the features they are not composed by each other, what hurt anything, right? So I can always apply.
Yeah, there is. Okay.
9020.
So you're a master's.
Yeah, I already applied in transfer program, but that was now. So
You already know me by this one.
yeah, I have to tell you.
What's your name? Yeah. You want to write it down? We're still working on it. It's going to be hopefully next few days, next week, or maybe 2 weeks of those things.
difficult just to give me a bird rule.
So you haven't done that too much.
Yeah, but I have
Transfer.
for the regression. Support that I can use.
Should actually. Consultation, yeah. I forgot to set up consultation. I'm going to try and get a consultation. So I just have to find the room.
Okay. Let's re-go. Let's resume. So as probably many of you know, there's an idea called correlation, and that's very closely related to what we're going to be doing with regression. So we have this correlation coefficient. Correlation coefficient is -1 to +1. It's a useful measure, but it tends to get overused. All it means is that if there is an association between a pair of variables, and it's only defined for pairs of variables, and the scatter, that's the spread in the association, is not too high, then you will get an indication of correlation. So high values. So if high values of x are associated with high values of y, low values of x are associated with low values of y, and the scatter is low, right? So there's not much variation in these. Then we say that these are positively correlated, and the correlation coefficient that you compute is going to be close to 1. If you do the same computation and you get a correlation coefficient close to -1, the position is the same but just inversed, right? So or inverted, I should say. So high values of x are associated with low values of y, and low values of x are associated with high values of y, and the scatter is low, right? Then it'll be -1. If the scatter is high, then it means there's no particular association between the values. They kind of go up and down without any dependency, and there's a large scatter. So this should only be used when x and y are approximately linearly associated. So if it's nonlinear, it doesn't work. And the formula, which is called Pearson's correlation coefficient, which is widely used in many domains, is this. So you have the covariance of x and y, we'll explain what that is, over the product of the square root of the independent variances. So covariance, just to kind of make clear, is this idea here. The covariance is the key idea in regression. So covariance means, basically, qualitatively, it means when you have two variables, then x and y, two variables x and y, when they move together, then the covariance is high. Otherwise, if there isn't a particular association between them, or there's a lot of variation, then the covariance is not high. The denominator is simply acting as a normalizer. Well, let me just go back. So the denominator here, the two variances, is that's this here, this product here, is simply acting to, as it were, normalize in terms of the standard deviation. Okay, so the standard deviation or the variance is high. This will relativize or normalize the covariance. Okay, so it's the covariance, how much they move together relative to how much each of them moves individually. And the covariance is like this. So we have xi minus the mean times yi minus the mean. So let's just think about this for a second. What does this mean? Well, so we have the mean for each of the variables, And we say, okay, well, if it's above the mean, then this is going to be positive, and this is above the mean at the same time. This is I for I in our data set. Then this is going to be positive. If this is below the mean and at the same time for the same data point, this is below the mean, then that's also going to be positive. And you can sort of reason about the other cases. So what does the covariance mean? So case one, what we said, they're both above the mean, or they're both below the mean for case two. In the first two cases, that's what we mean by vary together. So they're both high together relative to the means, or they're both low together relative to the means. And they're not covarying in the other two cases, right? So when they're going in different directions. And this is a sort of very intuitive argument for the fact that they're not related, or they're not likely to be related. Okay, I just want to speed it up a bit. So I don't think there's too much that I want to say about this slide. You can read it offline. You may have heard of the problems with Pearson's correlation. I'll just mention them very quickly. Because the correlation, and this is also true for regression, because the correlation looks at the actual values, well, this is the difference in values, you can see effects, or this can cause, there can be some issues, let's say, if you're dealing with numerical differences, okay? If your data is just pretty rough and ready, and let's say the X range is much higher than the Y range, just to take an example, then the effect may be reduced. They may actually be correlated, but the effect may be reduced. One way to get rid of that that's commonly used is to look at the ranks. Okay, so if it is above the mean, you just say +1. If it's below the mean, you say -1 or something like that. Or this one is above that one, more correctly. That's a kind of robust correlation. Okay, and I'm taking a little longer than I hoped to get to the regression. So I want to just mention something here. So if you're doing sampling and you can assume a normal distribution, is what this slide says, and the data set is sufficiently large, then you can apply essentially statistical test and see how likely it is that your correlation can be true. So this is just what applies in the case of computing correlations. This is the case for many statistical tests. You can look up and you can estimate statistical significance. It may or may not be important for what you're trying to do. If you are trying to do correlations, and there are many tools available to do this, and they will give you statistical confidences, just bear in mind it's a useful pre-processing step, but just bear in mind some of the issues with correlation. Okay, so just on correlation, and we'll then get into regression. So what's the point of correlation? It means that it's true, or correlation should be found if there is actually some association according to the correlation coefficient between X and Y, and the direction will tell you whether it's proportionally or inversely related. And then the size of the number tells you about the scatter. So you're only going to get a high correlation if there's not very much scatter. It's important to note that it doesn't tell you about the relationship in the sense that regression does, which is what's going to differentiate regression. So they're based on essentially the same sort of ideas, but it does not give you a way of computing y given x or x given y. So don't use correlations to compare data sets. All that you can say is this, well, there seems to be some positive or negative correlation. And very important, you don't use correlation to imply that X is somehow a cause of Y, or Y is somehow a cause of X. You may or may not have seen that before. If you haven't seen it before, well, now you have. All right, so we finally get to the topic, but there was a reason why we went in a roundabout way, and that's because essentially pretty much all the machinery that we need to define and derive regression is now in place. Yeah.
Of correlation.
Yeah, for example, okay,
No, you wouldn't normally. If you're going to do regression, as we'll see, you just do regression. You sometimes want to do correlations. Some people are interested in correlations. There's nothing wrong with doing correlations. I don't mean to say that it's a waste of time. The reason why I've spent so much time on it is that underneath regression is essentially the same machinery that is in correlation. Does that answer the question? Not really.
no, what I understood is that, like, I can forget this. There's no use. Or what
No, don't forget it. I mean, okay, why? Perhaps come back and see me at the end and say, I still don't get why you told me all that stuff about correlation. Well, hopefully you will. Right? Okay. Any other questions about what we've looked at so far? Okay. Okay, so this mic seems to be working, so I'll use it for a bit until it seems to be quite intermittent. It seems to come and go. All right, so in the basic setting, I spoke too soon. In the basic setting, we've got two variables and data points representing them. And the question is there a relationship between them? And the form of the question can be made more sharp by saying, are they linearly related? So can we draw a straight line just as we had at the start of the lecture? So, and maybe this will answer your question. So if we got a correlation coefficient between x and y, that would suggest that the answer to this was maybe yes. But remember, the correlation by itself won't give us what the relationship is, or won't give us the form of the relationship, and won't allow us to do any prediction. And if there was such a relationship, we want to know what it is. We want to know what the linear dependence is going to be. So let's say that let's say that we actually did do a correlation and we said, oh, this looks like there's a linear relation. We should be able to find a line. We should be able to draw a line. But then the question is, well, what line should we draw? And this is a fairly typical question. All right, so we've got a dependent variable y, or a thing that we're trying to predict, and we've got the x variable, which is, if you like, our input, and we have the data points x, y pairs, and we have this idea that for any line we can find the sort of distance from the line. Here we're just denoting that d, and we'll say that we could, by the way, just take the absolute value of this, but by convention we take the squared. That will give us the least squared estimator that we talked about back at the beginning. Well, it turns out that, and this is where the correlation, I think, comes back in, that I can tell you that the regression coefficient is defined in terms of the covariance and the variance. Okay, so this is what we had before. And this can be simplified, and it can then be written in terms like this. All right, so how do we get to this point? Well, before we do that, let's be sure that we know what we're talking about. So B, the regression coefficient, it means that when x changes, specifically when there's a unit change in x, then B tells you what the change in Y should be. So if you increase, let's say, X, the X changes by 1, let's say, then B will tell you what the change in Y should be. You can also interpret this as saying, if the values of X were assigned at random, then B estimates the unit change in Y caused by a unit change in X. Now, causality is a bit of a thorny issue, but you can make this causal interpretation. If they were not assigned at random, so they came from some other source, then change in Y will include the change in X and any other confounding variables that may have been affected by Y and may or may not have been measured, certainly are not in your linear model. And then B, if B is 0, then there's just no linear relationship. And then the best thing that we can do, well, there is one thing that we can always do, which is take the mean. Okay, so the mean of the values of Y is the best that we can do if there's no linear relationship. So that actually is another justification for taking the sample mean. So what's actually going on here is that we have the model that we set out with, the regression model, the probability of Y given X, and there's a distribution on all of these values. Okay, so here's the line that's fitted. Here's the true line with a mean and a distribution of the values. The values that we see are sampled according to this distribution, and the true thing that we're trying to estimate is the expected value, which is equal to these two parameters times X. The actual thing that we get is Y hat, not the expected value of Y hat, which is equal to A, which we have to estimate, and B. Okay, so that's the difference between that's the statistical problem. That's the inference problem. We have to find what those are. So we proceed as follows. We obtain Y's for many instances of X, X1. So we get values for Y, and that will allow us to get P of Y given X1, P of Y given X2. So we assume that all of the Y distributions are the same and they have the same spread. And then for every P of Y given Xi, the true mean lies on a straight line. This is the true regression line. That's the regression model, and that's this thing here. So the standard terminology is that the yi's are IID, which is independent and identically distributed. So they're independently drawn according to these identical distributions. That's what these are here. And another way of saying this is that any individual Y is equal to alpha plus beta, which are the true parameters, times Xi, plus some independent errors. So these are normally distributed with mean 0, so that means they're just located on the true regression line. So it's a Gaussian distribution centered on the true line, with this with the same standard deviation or variance. Okay, so when we're doing the estimation, what we're really talking about is the bias and variance of the estimates of A and B. Now, the assumptions, under certain assumptions, the least square estimates of these values will be unbiased and will have the lowest variance. And there is a theorem which we're not going to go into, but this is true. if the expected value of the residuals is 0, and we'll talk about that. The spread is constant for all the residuals, so the variance of these errors or residuals. There's no relationship between them, so there's no covariance. We know what the covariance is. And there's no relationship, there's no covariance between the points and the residuals. So it's just truly random noise. Okay, so here's the idea in a nutshell. I have a hidden regression line. It has these parameters alpha and beta. Any x value is drawn according to alpha plus beta times my x value, and then I add on this normally distributed noise, and there's no relation between residual for one point and another point, and there's no relation between the residual and the point at which I'm currently looking at. And overall, the values of the residuals, their expected value is 0, so that means there's no bias above or below the regression line, and they all have the same standard deviation. So if these assumptions hold, then the expected value of my A parameter, which we're going to derive, is alpha. The expected value of my B parameter is beta, so these are the true values, and the variance will be the least in these estimates. Now, actually what I was talking about before is this. So when I make this assumption that residuals are normally distributed, so if they're a Gaussian noise, then it turns out that least squares estimation is equivalent to something called maximum likelihood estimation, and we'll show that later on. Okay, so let's just proceed, and we've said all the groundwork, we've got all the statistical considerations out in the open. Let's just proceed and see what can be done in terms of this. So let's say we have a relationship between, we have measures on height and weight of some bunch of people. We've got n of these, and we want to model this as follows. We want to have a linear model where the weight is equal to some value A plus beta times the B times the height. And we want to make this a regression, so we want to find A and B such that the sum of squares, the sum of the squared residuals, so the error is minimized. Okay, so with reference to this particular example, this is what happens. Okay, so here's our objective function, or our loss function. So weight, which is the actual weight, times the predicted value of this regression model, A times B of the height. So first off, let's take that and take the partial derivative with respect to A and set it to 0. We're going to get this. Let's take the partial derivative of B and set it to, that's the same objective function, and set it to 0, and we're going to get this. So the solution to this problem is this. The weight equals A hat, which is the estimated value here, and plus B hat times the height, where B hat is this thing here. And we can write that as this. So the mean of the weight plus B hat times h minus the mean of h. Okay, completely clear? Possibly not. So at this point, what I thought I might do is to try and show you some of the steps in this derivation. So it's not difficult, at least once you've seen it, but I made some notes and I'll try and show you, I think, what are the key steps. So I'll just switch to the document camera. All right, so I'll see if I can just give me a second. I'll see if I can adjust this. Right, just as a sort of explanation of why I think it's interesting to do this, you see this derivation that I just showed you on the slides in many places, but you don't, I think, always see the full derivation. So if my notes are okay, then we should be okay. Now I'm just going to change the terminology slightly. In fact, I might try and move this camera a bit more. Okay. So what do we start with? Well, we start with a linear model. And we have a loss function. So the loss function, remember we talked last time about the loss function. Can you read this? No. Loss function. So we'll call the loss function. Well, let me go to a simple version of this. Okay. By the way, I'm just going to change notation. Instead of A and B, I'm going to do this. So we have two coefficients. So this is for linear regression of two variables. Can you read it? Yeah. So we have, so y is going to equal coefficient W0. I'm using W because that stands for weights. And then W1, and we'll call that x. Okay, that's going to be my notation. So I've already showed you different notation in the slides, but everywhere you see this, the notation's slightly different. So, if you're familiar with y equals mx plus c, or y equals a plus bx, it's all the same thing. So the loss function is going to be, something like script L equals 1 over n, and then we sum. And I'll just do the indexing using little n. Okay, so we have y, little n. That's the value of the function in the data. And there's n data points. And then the model will be w, weight 0, that's the intercept weight. That's your a or your c or whatever you want to use. Plus the product of W1 and the nth value of x. And then we need to close the brackets and square the difference. Okay, so that's just your mean squared error. Mean squared error. So sum it up. And so that was the business we did about the mean before. Okay, so I'll do one more step to sort of see, so you can see where you start with this. So the first thing you do is the expansion. right? So you're going to go y sub n. I'll just close it up a bit. Keep an eye on me because I'm probably going to make a typo here. Just start, this is how you would start. Plus. Okay, that's just expanding that out. So the whole bunch of steps as you expand it out, and you get, and then you do some rearranging, and you get to a point where it looks a bit like this, or it looks like this. Okay, so I'll use some square brackets, I think. So you have terms like this, w1 squared xn squared plus 2 w1 xn w0 minus yn. You could do this yourself. It's not hard. It's just tedious, so that's why I'm skipping it. Plus w0 squared minus 2 w0 yn plus yn squared. I think I've got them all. Okay, so that is just the same loss function as we had. Nothing has really happened yet. We've just expanded out and done some reorganization. So we say let me just check. I think it's all there. So at a minimum, right? So we want to minimize the least. We want to find the least squares solution. So at a minimum of the loss function, we want the partial derivatives with respect to the coefficients. They should be 0. There should be 0. I'm not going to bother with the second derivatives, but you can go ahead and do the second derivatives and find out that, in fact, there is a single minimum, which is a nice property of this. It may not always be the case, but for this, it is the case. So let's go for which one did I do? Let's do W0. So we'll take away any terms from this loss function expansion that don't include sorry, I'm doing W1 first. So remove all terms not including W1. Okay, so then we get something, or we get this. N equals 1 to n. So we have W1 squared xn squared. We have 2 W1 xn x0. There's a bit of, multiplying through here, but that's all. And then 2 W1 xn yn. Now, there's a rearrangement which is useful. So So the rearrangement here is taking terms not indexed in the summation, so that's by n, little n, outside the sum. So sorry, which line? This one?
After extent, the next one,
Sorry, thank you. Thank you. Yes, you're absolutely correct. Sorry, let me make that clear. That should be W0. So yeah, so taking the terms outside the expansion, taking the indexing outside, taking the terms that are not indexed outside the sum, because that's not going to change something. So then we have 1 over n x, yep, xn squared. So I might just bracket that, and then 2w1, and then the other. So we've got sum n equals 1 n, and then we have this xn w0 minus yn. And now we take the partial. What are we doing with respect to w1? So can fit, is this going to fit? Yeah. W1. So 2w1, 1 over n, sum n equals 1 to n, x n squared plus 2 over n, sum to n, xn, w0 minus y1. Close that off. Okay, and looks like I didn't do that one. Okay, so let me, oh yeah, here it is. Actually, yeah, I see what I've done. I actually did W0 first, so let me, let me do that. And we'll come back to this. So going through the same steps for W0, I'd get to the point where I'm doing a partial derivative with respect to 0. So so I'm not going to do the derivation, but it's using the same idea, getting all the terms that don't involve W0 out. Oops, sorry. Okay, set that to 0. And we're going to get 2 W0 is 2 over n. Got sum n equals 1 to n. yn. W1, 2 over n. xn. And then we have 1 over n. One to n, yn, minus w1, xn. Okay. Now, when we look at this, we start to see something a bit like we saw when we were looking earlier at sampling and correlation, in particular correlation. So what we can do is the following. We can write something like this. We'll say y bar, or the mean, is 1 over n, sum to n, yn. And we can say x bar 1 over n sum to n xn. And then we can rewrite our the thing we had up here when we took the partial and set it to 0 as this. W0 equals, so this is now y bar minus W1 x bar. Okay, so now this is looking a bit like something useful that we could actually use. I'm just going to put a hat on W0, and time's getting ahead of me, so I won't continue the full derivation of the partial derivative that I started for W1. I'll just write down I'll just write down the last bit.
So you're going to have to believe me. Let me just sort of magically... We started it, but we're going to get to a bunch of stuff. We're going to get to this, 2W1. In fact, I'm going to have to skip a bit more. Okay, so 1 over n sum to n xn squared minus... This notation is just the same thing that we did when we did the W0, right? So we're getting rid of a whole bunch of summations and taking the mean, essentially. Plus, and more of the same for y and x in product. And then, if I can squeeze this in, 2, 1, sum x n y n. And yeah, so basically what we would have had to do is just a bunch of the expansions and reorganizing just as we did for W0, but it's a bit more involved. Okay, so let's look at this. So what we have now is, again, we can do the same for this, and we can do the same for this. Set them to 0. And again, without going through all of the steps, you'll end up with this. So you've got W1. Again, I'm going to put a hat on it because it's the estimate. So I have the product of I have the mean of the product of xy, minus the mean of x times the mean of y over the mean of x squared minus the mean of the squares minus the square of the means. Does that ring a bell? Well, I know it was about an hour ago, but what we have actually got here, and I'll leave it to you to kind of compare, is the variance, and this is the covariance. X and Y, obviously. Okay, so that is essentially what we saw earlier. And the last thing to say is that we had, remember we had W0. That's why I put the hat on it. We put W0 in with its hat, and we take this W1 that we just derived and we insert it into here. And this W1, which we've just derived, is the covariance over the variance. And if you look back in the earlier slide, you'll see that that's what we said was the regression coefficient. We use the letter B instead of W1, but it's the same idea. Okay. Well, I hope that helped. I feel it helped. I mean, it helps a bit. It certainly helped me when I was learning this stuff. I hope it helped you, because what I'm trying to show here is that the derivation is simply is straightforward from the definition of the MSE loss function. All we did was expand the loss function,
We then took partial derivatives of the two coefficients that we need to solve for, set to 0, and we derive the expression first for W0 and secondly for W1. And once we've got that, we plug that into the expression. I also think this is easier to see when you look at the more complex multivariate version of this as well. Okay. At this point, I think we're just after 8, so let's take another short break and resume in about 5 minutes. Yes. Yes, yes, it should. It should be, yes. Yes. I was saying like minimally. Oh, yeah, go ahead. Yes.
I want to know what's the difference between the squared residues and the mean square. It seems
Same thing, except, yeah.
Square.
What's this?
Oh, it's the partial derivative.
Oh, right. Okay. Yeah, the residuals are the errors, right? So you take the square and you take the mean, and that's what you're trying to minimize.
So they're the same thing. Yes.
No, well, the squared, so if you add all the residual, if you take the square of the residuals, add them all together and take the, and divide them by n, you get the mean square.
Oh, I should sum it.
Yeah, so the residual is just the difference between the thing you predict and the actual value.
Yes.
Take the square of that and do that for all the data in your data sets, and take the average of that. That's the mean squared error.
Yes. Yes. So, because I was learned the Andrews machine learning for this course.
All right.
Yes. So,
So what does he refer to?
yeah, this kind of
Same thing.
yes. But I don't really understand before this linear regression. You told us they expect and there's something else like
Expectation.
Expectation, yes, like this.
You should think of the expectation just as the mean, like the mean.
Okay, I should know the meaning of the expectation, but I don't need to use the meaning.
The expectation is the expectation is this idea of what the value is for the whole distribution, right? Which you don't know. So you can think of it as, for a sample, it's the same. The mean of the sample
is an estimate of the expected value of the distribution. So it's like the perfect thing that you don't know, and the actual thing that you have in your data set in your computer. And you're trying to use the mean to estimate the perfect thing, expected value. So that's the definition.
I'm going to annoy you this evening. Is that correct to say that if X and Y are very low correlated, so it's hard to model or predict? And if X and Y are highly correlated, it's possible to model and predict?
It's so if you get like close to 1 or close to -1, you should be able to find a good linear predictor.
Okay, so because of this is possible, right? I
Yeah.
cannot assure 100%. So the matters now, if it's linear regression, which function to use? If it's linear, quadratic, something like that.
If, according to the setup that we have, if the correlation is good, like it's a high number, that means that there is a linear relationship, like the covariance, they co-vary, either together or inversely, and therefore you should be able to find a linear regression which maps one in terms of the other given these coefficients, and it should be a low error regression.
So to find this correlation within the training set should be the first step, right? To see if it's possible. If it's 0,
If you're doing this in practice, that will be a good first step.
okay.
Yes.
All right. I was making sense.
Yeah. Because the coefficient that we just derived is essentially the same as the correlation coefficient.
Yeah.
So it's in terms of the covariance and the variance. That's what we're trying to do.
Okay. All right.
Okay?
Good. Thank you.
Okay. So we're not gonna do any more derivations in this course. At least I don't think so. Well, we may do one, but and someone has pointed out to me that there are a lot quicker ways of doing the derivation, which is true. What I was trying to show there is simply that the steps are straightforward. And really the only assumption is how you take care of the averages. All right, so I'm going to assume that we're now pretty clear about where linear regression comes from, and essentially how the coefficients can be computed. I should say that in practice, I mean, you could do linear regression by, using the version of the coefficients that we've got here. By the way, I'll just flick back a second. So like here, like here. So these are in terms of the particular variables, weight and height, but you can generalize those to being x and y. Y and x. So you could just plug these in, and you can find these like this. In practice, in implementing it, you wouldn't do it that way, but that's okay. Okay, so here we're showing an example of that. Here we're showing a plot of that example. So we're now just going to explore some ideas that follow on from regression. So what we're showing here is the actual model for a particular instantiation of the values. The details are on the next slide, but the regression coefficient, the B parameter, hat B, is 0.78, so that corresponds to the slope of this line. The data were generated according to this with random, normally distributed noise, mean 0, variance 5, and that gives you this blue line. Well, it gives you the it gives you the data to which this blue line is the linear model, for which this blue line is the linear model. And notice here that if you take the mean of the data points, that's this orange line, so the red line is the true line, the blue line is the model for the simulated data with added noise, so that's why it's not the same. And then if you look at this orange dotted line, what you're seeing is the mean value of H and the mean value of W. So this is the thing we're trying to predict. And we note that it's on the line. So I'm just trying to find the values. So the average weight, 181 is the mean, and 74.5 is the mean. So the means are on the line. That's the line that's fitted. The means of the data. Okay, so as we saw in our, sorry, that's just the detail. I'll leave that for you to read offline. So as we saw in our derivation, the regression coefficient, which is the parameter that you multiply x by, is this, the covariance between x and y as a proportion of the variance. So here, the variance is written in an unusual fashion. It's written as the covariance between x and itself. So it's the same thing. Okay, but this is interesting. So when if we think about, remember we said that what the regression model is telling you is the change in y, and now we're going back to x and y rather than height and weight, or weight and height. Height and weight. So given a particular value of x, B tells you what a unit change in x will show in terms of the change in y. Now, in terms of height and weight, these are not unitless measures, so we have the units of the covariance are units of x times units of y. So x was height, so that's in meters. So the covariance is meters times kilograms. The variance in x is meters squared, because of this. And the variance and their quotient is going to be, so this divided by this, so that's, let me get this right, meters times kilograms divided by meters squared, so that gives you kilograms per meter. And that makes sense because of what we said. The change in y is reflected by the regression coefficient times x. So for a unit change in x, that will tell you, the product of those two things will tell you the unit change. So y is, so the regression coefficient, the units of the regression coefficient are kilograms per meter, if you want to interpret it in that way. Okay, so that's very nice because that gives us a direct interpretation, at least for univariate linear regression. So we can think of what what effect that would have. Now, that could be useful, and in fact, this is quite widely used in applications. So you might, you do the learning, you fit the model, and then someone might say, oh, so you're telling me that, let's say you were fitting, I don't know, well, let's say weight and height for, I don't know, maybe you're a farmer, right? And you want to know if the height changes, then this is what the weight is going to be, because, I don't know, something's happening with the data. So you say, oh, okay, so if they change this much in height, then they're going to change this much in weight. I just thought of another example. So say you're modeling, I don't know, change in house prices. This is something that people always want to fit with linear regression. So they want to say, oh, okay, so you're telling me that my house price in dollars depends on, I don't know, the size of my house in meters squared or something like that. So if I make my house, 10 meters squared bigger, then I'm going to, see such and such a change in my house price. So that would be a potential thing that people might want to do. Now, you might not believe that, but it would certainly be modelable using exactly this framework if you had a whole bunch of data on house area in meters squared and prices in dollars. And so people often use linear regression for exactly that reason. They use linear regression because they want to maybe do that kind of modeling. Now, it may not be the best kind of model, but it allows you to do that, and other models don't, at least not in the same way, just because of the linear dependence, right? So if you had a sort of weird, if you had a weird sort of curve-fitting model, it would be a bit more complicated. So a nice thing about linear regression is that once you've got the model, then as long as these variables' dependencies make sense in some physical sense, then you can make this argument. Okay, so let me see. Okay, so it's looking like we may not get through all of this this week. Anyway, let me keep trying, and if we don't, then we don't. There are certain things I want to pick up on, certain things, as I told you at the beginning, I'm going to refer to, but you don't have to, they're just there as background. So at this point, I do want you to pay attention to. So the intercept is fitted, or the value of the intercept from the fit is such that the regression line is going to go through a point which is the mean of both of the variables. You can show that pretty directly. I'm not going to do that now, but so if you add a constant to the x values, which is just like translating those values, that will affect A, that will affect the intercept, but it won't affect the regression coefficient. So the line, that function will stay the same. And that should be clear because, as we saw, the regression coefficient is just defined in terms of the covariance and the variance. So distance from the mean. So the x values could be zero-centered by just subtracting the mean, and then the intercept would be equal to the mean of y. And then you could even subtract the mean of y from all the y values and get a zero intercept, and essentially the problem would not change. Yeah.
Can we interpret this alpha as whatever is not explained, like in your example of the house price, whatever is not explained by the square meters, but is explained by some other variables like location and so on and so forth. So everything that our model can take.
Yeah, the residual. I shouldn't say residual, but yeah, the rest. Or just the, yeah, it's kind of like the inherent, it's like the inherent offset, if you like, of the, what was that example? Dollars and meters squared, the inherent, yeah, offset from. Right, so, yeah, I mean, if the intercept is zero, then it's just there's no sort of shift. Okay. Right. A lot of these things I put in, you can read them. They should make sense given what we've already developed. I'm not going to go through this because I'll just be reading off the slides. It's just there for you to read. This is just recapitulation on what we've just done, but I do want to pick up this point. You can check this for yourselves, but remember one of the criteria we mentioned before was that the sum of the residuals is going to be 0, and this is a straightforward consequence of the regression equation as we've derived it. But the reason I wanted to draw your attention to it is that it's one of the characteristics of regression that you fit a line to all of the data, and because of the way we've set it up, then the residuals are going to be 0, the sum of the residuals is going to be 0. So that means that every point is going to have its effect on the regression line, and in particular the regression coefficient. And that can be good, but it can also be a problem, particularly if there are outliers. So if there are outliers that are way off, they have to be included in the model, right? There's no way of removing them. They have to be included from the model, and particularly because we're taking square distance, square error, they may have a considerable effect to change the structure of the model. Now that could be a problem if they really are wrong, right? If they're outliers because actually the data should have a certain number of outliers, then that's the correct thing to do. If they're outliers because of a mistake or just something that shouldn't have been there, then that's a problem. So here's a small example, and here, again, this is explained on the following slide, but here the green dot is supposedly someone whose weight was written down wrong. And so here's the red line and the blue line that we had before. But the effect of this error in the data is to, in a sense, pull the regression line that's fitted, which is now shown by a green line, and it's changed the regression coefficient. In fact, because there's only one of these, and it's, I guess, maybe not really way off, the regression coefficient hasn't changed too much, but it will cause a change. And this is a consequence of, as I said before, regression fitting all of the points, and you know, all of the residuals have to be in the model, and you minimize over all of those. Okay, so I think we now need to get on to, oh, right, one more thing before we get on to multivariate regression. Now, so we spent a lot of time setting up the framework, and we showed by deriving, so setting up the loss function to be minimized, you know, taking the partial derivatives, setting them to 0, and getting an analytic result, which is very nice that you can do, because it shows that that's actually going to be the minimum, right? So that's the thing we wanted. That was our specification. It's not the only way to do it, and we'll come back to this later on, but I just wanted to point out that we could do an alternative approach. And in fact, it turns out that for many possible loss functions and model classes, it's not possible to do the full analytical approach. So you can't go through, at least, or certainly not easily, and do that derivation. I should say that there are now very powerful frameworks which will do the derivation for you. So that's not so much of an issue, but underneath it all, whether or not you can do the analytic approach is an important consideration. So let's say you didn't do that. The question is, well, could you still learn a linear regression type model? And the answer is, well, yes, you can. And it introduces the very important idea that we'll see later, which you may have already come across, which is gradient, finding the gradient and building an algorithm that exploits the fact that, so you're trying to minimize, if you can find the gradient or derive the gradient, you can recall that the gradient vector will point in the direction of the greatest increase of a function, and if you're trying to minimize, you should take the opposite direction. So finding the gradient vector will also tell you where to go to minimize. And essentially, the rule is something of like this form. We've got two, in this case, we're just doing a linear regression for a single variable x and y. So we've got two coefficients, the intercept and the regression coefficient. And it's an iterative algorithm. So this idea is very general. In this case, we've got the gradient for A and B. This is sort of non-standard terminology. We have a small sort of fudge factor, or it's sometimes called what's usually called the learning rate. And what we want to do is adjust the current value of BI in the direction or the opposite direction of the gradient multiplied by this factor, which is usually less than 1. The reasons for that will become clearer later when we talk about this. And we keep doing this iterative scheme until basically things don't change much. And that suggests to us that we've reached the minimum or close to it. So this will actually work pretty well in the case of linear regression. Why? Well, we mentioned, we didn't go to the bother of deriving it, but we mentioned that in actual fact, because the second derivatives, we mentioned that the minimum we find is the global minimum. So this will actually get you close to or at the global minimum as well for linear regression. For other more complicated things, there may be more than one minimum. That's to say, there may be local minima, which are not the global minima. In that case, the best that you can do with this kind of scheme is end up in one of those local minima, which may not be too bad if the local minimum is not too far off the global minimum. But this idea is actually very general, and it's the way many algorithms in practice, or some variant of this, is the way many algorithms actually work in practice. Okay, so that was the last point I wanted to mention on univariate linear regression. Now, multivariate starts to get more complicated. So here I'm going to show you some of these starred asterisk slides. And there, as I said, this is background. I don't expect you to learn this. It's there, as I said, it's useful background, it's useful to know, and if you're interested, it's there for you. So multivariate regression, let's just motivate it quickly. So the reason why is that the dependent variable y, the thing we're trying to predict, could actually depend on the values of several variables. So in a medical application, there may be different rates of the dependent variable depending on, let's say, gender, or you know, in terms of the house price thing, it may be related to, you know, being close to a particular kind of facility, like a school or a park or you know, the center of the city or something like that. Now, you should have that in your model because it is important to get the correct value. If you can still have alternative ways of adding that information if you don't have the actual variable you want. But and importantly, if you're going to do statistical confidence bounds, this can give you a better confidence bound. So the multivariate model is just a straightforward extension. So we have, so this is the regression model, the ideal model. So mu is beta, which is the intercept. And then there are a bunch of variables, and there's a single variance. So these are independent errors with mean and variance. So this is exactly the same idea that we had before. But now for multivariate, and we estimate the y hat, and these should also be estimates. Now the derivation is actually, if you do it the way we did it, very complicated, but that's not the way that you would actually do it. You would use a matrix representation. I'm just going to show you essentially how it's done. So this is what I mean by the asterisk version. So, you know, we're going to skip lightly over this. It's just there as background. So we need covariance. So here X is your data matrix. We're also putting the intercept in here. So we're using homogeneous variables. So X transpose Y is going to give you the covariances. What else do I want to say? There's a scaling matrix. Let me just refer to my notes, things I wanted to just highlight. Anyway, we're going to... Okay. So the point that you get to is this. So now we have... and now we're using W for our weight vector of weights. So W hat is the thing that we want to estimate. So this is our, you know, A, B1, B2, or sorry, B0, B1, B2, and so forth, or W0 in my notation, W1, W2, and so forth. The W0 is going to have a corresponding X0, which is always 1, so in homogeneous coordinates. So X transpose X, take the inverse. Okay, so basically what the setup is the covariances that we had are, remember our regression coefficient was at the end of our derivation. So my derivation for W1 or W1 hat was the covariance over the variance. So the way to intuitively understand this is that this is the covariance, this is the inverse, and this is the variance. Hang on, I've got that wrong. My bad. This is the covariance. It's the covariance between all of the variables, the x's and the y. And then this is divided by the variance. So the variance in this case is just x transpose x, which you can think of as the square, and then take the inverse because, you know, you can't divide. Okay, so that's really all this is doing. It has some nice properties. If you do various operations like zero centering and the features are uncorrelated, it reduces to what was on the previous slide. So the way to think about this is just as the variance was doing in the univariate case, it essentially normalizes or decorrelates centers and normalizes the features. So with a little bit of hand waving, hopefully you can see the connection to the thing we derived. So think of that as the variance part, think of that as the covariance. So what the fit for the multivariate linear regression is finding a vector of weights to minimize the squared error according to this. Now, on the following two slides, there's a setup for two variables, but I'm not going to go through that. That will, again, if you feel interested and you want to spend some time, you can have a look at that, and that expands it out for two variables. All right, so in the remainder of the time, I just wanted to pick up on some further issues. Now, the first is an important and general one. So it goes under the heading of regularization, which is a kind of strange term. If you've heard it before, you'll know what it is. If you haven't, here's the idea. So regularization, the idea is to avoid overfitting. Now, I haven't actually said too much about overfitting already. Some people already know what it is because I've had a comment about it. Overfitting is the idea that you're getting too close to the data. Now, we'll formally go into it a bit more later. But we haven't said too much about prediction yet. I don't want to get into that in detail, but the idea is that if I have a complicated data set, then I can fit it arbitrarily closely by adding weights to key variables. Now, I just realized I should have probably said something about these variables. I'm going to say something shortly, but I think this I may have put the slide in out of order. I wanted to get this. Yeah, I remember now. I was trying to get two things in a different order, and I think I might have sort of said something about non-linearities before I actually meant to. Anyway, let me say it right now. So let's look at this data here. So I'm showing three regression models. Now I've actually got, this is a linear regression obviously, but I've actually got non-linear regressions here. And I haven't said in detail how we do that, but I'll just say that now. So what we can do is we can add higher degree polynomial terms into the regression equation. A number of ways in which we can do that. There's a general approach which I'll show you shortly. But why would I want to do this? Well, if you look at this here, it looks as if you would actually need higher order terms to fit the curvature in the best possible way. Now here's the problem. I can continue adding these higher order terms and many others, in fact. But would that be a good idea? Well, maybe. If I really believed that this was actually the data that I wanted to fit and only the data that I wanted to fit. But in general, this would probably be a bad idea because this may actually, these guys here may actually be due to noise, and in fact, a linear model is what I want, right? So a linear approximation to this data may actually, on unseen data, for prediction, do better. This data, though, I'll get lower error if I start adding some of these more complex terms. So what's regularization? Well, regularization is the idea that you not only try and minimize the error when you're trying to fit these coefficients, but you also put a constraint on what's called the complexity of the model in some cases. Specifically in the case of regression, that means not letting the coefficient values get, quote unquote, too big. So this is actually a powerful and general idea, but the method, at least for regression, is very straightforward. You simply add a penalty, and now we're talking about so the optimization that we're trying to do is not just minimize the error, but we're thinking about a more general idea of minimizing cost. The basic form of linear regression, in the basic form of linear regression, cost is just error, right? That's what this is here. So MSE as a cost function, if we're given a bunch of data, we simply say that this is the function. So theta here just denotes a function with parameters theta of the data xi, take the average over all of the data points, for the squared difference between the value of the thing and the actual values. So note here, let me just emphasize this. So here, this is the fit of, when I'm using f, this is not the f that we had as the ideal function before, this is f theta, so we have n coefficients. Here there would be 4, here there would be 3, and here there would be 2. Yeah. Okay, that's a bit weird, but I think you get the idea. 1, 2. Yeah, that's a typo. Anyway, that's not important. There are a number of coefficients. This is the function of those variables, and we represent that by f theta. So the cost here is just mean squared error, but we can, because this is a function of theta, we can also do the following. We can say, oh, not so fast. Yes, it's important to minimize squared error. So we want to minimize cost, we want to minimize squared error, but also add in the values, or well, actually a function of the values multiplied by this constant lambda in this case, or it could be some other function, of the thetas. So the thetas, theta I, we have n variables. These are the coefficients. So what's going to happen here is that if I get a very low error, but for some reason I've got very large values of these coefficients, this cost is not going to be as small as an alternative case where I have an error that's maybe not quite as low, but I have smaller values for the coefficients. And in particular, let me just flick back to the previous slide. In particular, if I have fewer variables that are in the equation, and a way of doing that is to have a complex equation where some of these coefficients are 0, so they don't have an effect on the linear model at all. They just don't. This would be a nonlinear model. They don't have an effect on the regression equation at all if they're set to 0. That means effectively those features are not included in the model, and they go away, or they're penalized, right? So we pay a cost for having large coefficients. So we pay a cost for having many coefficients, and also if the coefficients are relatively large. So just one more time. This, in terms of the penalty on the coefficients, would be small if B and A are, well, let's say all the A's and B's are the same size. This would be small because there's only 2 of them, whereas this would be larger. So this is a better fit. It would fit better, this curvature, but it would have a larger cost in terms of taking more variables to do that. And because these are higher order terms, it actually could make sense to either reduce them to 0 or have them only having a small effect on the model, so being approximately linear. All right, we'll have more to say. Oops. We'll have more to say about cost functions and cost functions of this form regularization and so forth. And we can also do this with gradient descent, particularly by taking the gradient here, which is what this means. Okay. And there's a version of this, again, I should have put the asterisk here, but because I had the asterisk for the matrix vector version of this, I think you can carry that over. So the regularized, so here's our matrix version. This is least squares, so this is the same thing that we had before. And here's the version with the cost. So the only thing to note here is that now, because we've got a vector of weights W, we take the size of the vector, that's what these double bars are, or if you haven't seen this before, this is also referred to as the norm. So the bigger they are, the bigger this value will be. Take that squared. Lambda is the lambda. Oh, sorry, I didn't mention what lambda does. I should have mentioned that. Okay. Lambda, the point of the lambda is to allow you, the user, to tell the minimizer, right? So you're trying to minimize, the algorithm's trying to minimize this cost. The point of the lambda is to say how much of an effect, how much of a penalty you want the system to pay for this term. So if lambda is large, these are going to have more of an effect, right? So you say, no, 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 I definitely do not want a complex model, and I'm telling you that by making lambda large. On the other hand, if you're not that concerned about a complex model, you would make lambda smaller, and they would have an effect, so you'd pay some cost, but you know, relative to the error, it may not be small. So the point of lambda is a parameter that balances the error part of this cost function with the complexity part of this cost function. So the lambda here plays the same role, right? So here's your regression, here's your error component, here's your complexity component, the size of the coefficients. Lambda is going to balance that in terms of the cost. Lambda is a scalar determining the amount of regularization. Now, there are different forms of this kind of regularization. You could, so here, this norm here is it's actually within this, it's a sum of squares, right? So you square all the values and you add them up, which is called the 2 norm, and this is actually squared as well. But you could just take the absolute value and sum them up, and this is called the L1 norm sometimes. It's also, and the method of regularized regression. So regularized regression using that version on the previous slide is called ridge regression. Regularized regression where you just say, oh no, I don't care about that. Just you know, add up the size of the weights and penalize on that basis. That has a subtle effect. We don't have time to go into it. It actually means that the optimization will tend to drive some weights to 0. And that is sometimes important for people because when the weights go to 0, then effectively the features are totally uninvolved in the solution and you can throw them away. And if you're trying to get, you know, if you have a very large number of features and you're trying to get a robust model, then you would throw them away, and that could be a good thing to do. Okay, so we talked about the change in y depending on x according to the regression coefficient. This is the same idea when we have multiple variables. You can interpret the coefficients. So we've got 2 coefficients here because we now have 2 variables, and in general you have multiple coefficients. So B, as we said, for univariate regression is the change in y that accompanies a unit change in x. B1, so in general in the multivariate sense, the B1 is the change in y that accompanies a unit change in x1, provided x2, and in general all of the others, remain constant. Okay, so in general, Bi, where I is more than 0, is the change in y that accompanies a unit change in xi, that feature, and that's, you know, that's the regression coefficient for that feature, provided you hold all the other x's at a constant value. So if you want, remember we talked about that what if analysis. So if you want to do a what if, then you say, okay, let me consider adding these variables, or you know, do them one by one, and we can see what the effect of each one has. All right, so going back to what was we had the example of the house prices. So you want to say, well, you know, what if I do this? What's the effect on the price? What if I do that? What's the effect on the price? And you can see the effect of the change in that variable according to its regression coefficient, holding all the others the same. All right, so I'm just going through some issues that it's useful to know about. I think we may get, this may be the last one. No matter, we're pretty much through what we had to do, which is good, and I'll just cap it off at the beginning of the next lecture. So one thing you might be wanting to do is include non-numeric variables in your regression model. How do you do that? Well, basically you just use something that's called indicator variables. These are typically Boolean. So you could have something that was measured in your data but was not numeric. So for example, a Boolean example might be something, you know, high or low. So you could then turn that into a single Boolean, a single indicator variable that would have the value 0, let's say, if the qualitative variable said low, and 1 otherwise. If you had a 3-valued non-numeric variable, you could have low, medium, and high. So then typically what you would do is add, well, there are different ways to do it, but the easiest way is if I have 3 values, by the way, you could have done this with high and low. If I had 2 values, I add 2 indicator variables. One, it's 1 if it's low, and it's, sorry. The first indicator value is for low, which is 1 if the measurement is low. The second indicator value is 1 if it's high. We would assume that they weren't both 1, but you know, you never know, your data could be screwed up. So if there was a 3-valued variable, you would have 3 indicator variables, you know, 1 for low, 1 for medium, 1 for high, and so on. You can always take discrete variables and turn them into these indicator variables. So here's a medical example. If the patient takes a drug, yes or no. And then if you wanted to keep so D is whether they took the drug or not, and then you'd fit a model. So this is either 1 or 0, and you'd plug in the 1 or 0, and then you'd get the effect on the effect of the patient of doing this thing, you know, changing that to 0 or 1, and you have the same analysis goes through, which makes it useful. Now, this gets to, this is going to be the last slide for today because time's nearly up. And this gets to something I wanted to talk about, which I'll talk about next time, which is how to deal with non-linearities. We've actually sort of seen it basically in the penalty setting. But you may want to come up with a new variable